problem can very easily be described in kind of the Markov decision process type of framework. But we immediately come onto a problem, and this is that the state space to plan in for these vehicles is very, very large. This is because we both have many potential moves, so the action space per robot is very large, but also we have many agents possibly. But also because of the distributed reward around the crater, the depth of planning to achieve a specific task may also be substantial. So in other words, the state space can get very large for this sort of problem. So what we will do is we will illustrate an algorithm, in this case Monte Carlo tree search, which can help tackle these high dimensional problems. And we'll show how adapting the base form of this algorithm can be used to assist in collaborative tasks where coordination between multiple agents is important. So before I do that, and kind of we go in depth on both some of the background and also the specific implementation, just to get people excited. So here are some implementation. Oh, the videos aren't playing. I'm sorry, guys. So here are some interesting examples of MCTS being applied to kind of game-like situations. So we have here Mario being played very effectively. I mean, this seems like a very kind of masterful performance of the game using MCTS. And here, this is something known as the Miss Pac-Man competition, where essentially MCTS is being used to coordinate the ghosts to catch Miss Pac-Man. So we see that we're going to bring this up later because it's very relevant to our task of collaborative kind of coordination of agents. But this is another use of MCTS. And also interestingly, MCTS has been used to automate the AIs for a lot of real-time strategy games, such as here Rome Total War, which is kind of like a strategic game where one has to coordinate a lot of different units. So kind of an outline of our talk. I'm going to go into some of the background and building blocks that allow us to get to MCTS. Then Gabe will essentially be going over the core implementation and the kind of on a granular level of how to perform one of the key kind of seminal algorithms in the MCTS family. And then Jacob will be going over how we can expand this and introduce some varieties on the algorithm which allow us to extend this to collaboration. So before we go into MCTS, it's important to say, we essentially have a path planning problem where we have maybe, for now let's consider one agent, and we essentially have to plan how this is going to move in a specific space. And so we have a current state, and we're essentially, to plan, we have to expand a particular search tree, a decision tree, and then maybe decide on a specific set of actions. So we have a current state, and then our kind of search algorithm has to judiciously expand this search tree. So intuitively we might say, let's apply something which we all know, maybe A star. So just as a reminder, how a heuristic search method such as A star works, so we have some kind of search tree that we've maybe expanded. We've expanded to one node, and we have to decide which node do we decide to explore or expand and search next. And the way that A star works is we essentially search in the direction that minimizes the evaluation function, where that is essentially the sum of the cost so far to a particular node, and some admissible heuristics, where essentially an admissible heuristic is one that never overestimates the total cost to your goal. So in this case, very simply, which node would we choose to expand? The one in the middle, where it has a 5, and so we expand that, and then we can kind of iteratively expand our search tree. Now, for some simple task, let's say we have a specific location and we're going to an end goal, designing the heuristic seems easy. We essentially say something like the Euclidean distance is always going to be less than maybe the total distance that we have to traverse, and so it works well as a heuristic for this type of path planning problem. But does anyone see a problem for our type of task? Using A star? How would you choose a heuristic? What heuristic would you choose for kind of a distributed goal?
Euclidean distance.
But yes, but if we don't necessarily have some distinct goals, but it's more kind of distributed, that might be quite difficult. Yeah?
The sum of the Euclidean distances to each of the points?
That could be a very fair approach. If we have some discrete points, that may be a good way to go. But maybe if we have some kind of less discrete kind of distribution of goals, it may be more difficult to kind of design a heuristic that generalizes well.
Distance to the nearest one?
Yeah, I mean that could definitely work, right? But that may be so if you can imagine some situation where the nearest goal is not so valuable, but something that's further away is more interesting scientifically, then that might not work so well. So I mean, all these kind of heuristics could work, but we've already illustrated a problem. Within 3 minutes, we've come up with 3 perfectly reasonable heuristics, but we're really not sure if any of these is optimal in any sense, and if we change the situation slightly, we might have to completely redesign the heuristic and reevaluate whether the algorithm can work. So basically what we see is finding a reasonable heuristic is quite problematic. So what I'm going to show you next is that we can actually kind of learn what our heuristic is and the kind of the heuristic value at any particular state using random simulation. And that's where Monte Carlo methods come in. So I suspect that all of you will have heard of Monte Carlo methods, but essentially what Monte Carlo methods say is that you can estimate the expected value of potential future rewards from a particular state via random sampling of future moves. So essentially what this says is that if we're given a very simple situation here where we have to choose between moving right or left here, and we have to evaluate whether the state to the right is more valuable for our overall task, or the state to our left is more valuable. If we randomly simulate, in other words, we take a random walk from each of these 2 potential decisions, by sampling those enough times, we can ascertain some sort of value. So here with kind of a time window of 4 from that, so we iterate 4 random steps, we can see kind of one iteration how doing a random walk from the position on the right, you can imagine would, on average, give you a higher potential reward. I failed to mention that these blue circles are rewards. The larger the circle, the more reward. Yeah, intuitive. So essentially we can now use random simulation to ascertain the quality of any potential state that we want to explore in our decision tree. And so this is essentially a heuristic that we've kind of learnt by doing simulation. But now we've essentially introduced some level of uncertainty. Now that we're sampling, we don't have a kind of a deterministic analytical description of our heuristic, we have introduced some uncertainty. So we may have, again here have 2 decisions we have to make, and we've sampled each one a few times, but initially we've established some kind of mean reward from each of the potential states, but also there's some sort of uncertainty. So initially we say there's only 2 possible actions that we're taking, and we assume that they're normally distributed, so we have Gaussian distributions. So this is something that was very well explained to us in the previous lecture on how do we kind of differentiate and make decisions about where to explore in the adaptive sampling case. And so they introduced kind of the idea of searching the most promising direction. So in other words, exploitation, we want to search in areas that have got higher reward, but we also shouldn't neglect areas that we maybe haven't explored very much. In other words, kind of the theme of exploration. So the idea there was that we should use upper confidence bound, and we should always select the potential action which has got the highest confidence bound. So for a Gaussian, that's very, very simple. We kind of have the mean and some kind of linearly combined, so with some scaled version of the standard deviation. So here in this case we have a lower reward for the green, but you might conceivably say, we haven't sampled this enough, we have a high uncertainty, so it might still be useful to sample next the green state to find out more about it. But we might want to generalize to having non-Gaussian distributions, and that's kind of what the next slide is going to talk about. So let's generalize it a little bit further. We have many potential actions that we want to kind of search about. So like one of k actions, where we don't know the underlying reward distributions, but we've sampled from each of them. And so we need to decide what to sample next. And so the underlying distributions aren't Gaussian, but we can maybe make some kind of mild assumptions such that these distributions are bounded. And so overall, what we're actually trying to do is an optimal kind of search policy in a decision tree would minimize this value of regret. So regret is essentially, it's composed of 2 terms. The first term is kind of the maximum possible reward if you had always chosen the optimal search action, which would result in maximal reward, compared to the expected reward from whatever policy we design. And so we're trying to minimize this value of regret, which kind of represents the loss from not choosing the best action. So we need to kind of formalize this term of the upper confidence bound. So since we can't use things like standard deviations because we're no longer in the kind of the Gaussian domain, what we can use is something known as the Chernoff-Hofting inequality, which essentially sets upper confidence bounds for a wide range of bounded distributions. And so we say essentially that the probability that the true mean reward from a particular state being larger than our sampled mean and this upper confidence bound which we're trying to find is less than this term here. And so what we decide to do is we say, as we keep on progressing down the search tree, we essentially want this threshold to get smaller and smaller. So, as we progress with our planning, we want to become more and more, we want to essentially reduce the amount of uncertainty that so we want to search in a more refined sense, so like restrict our search. And so essentially this value, this probability here, we set it to a small value which decreases with every sample. And essentially, if you rearrange this and go through with the with a simple derivation, you arrive at the upper confidence bound. This u is this term here. And so we then, sum that to our original mean, and we get to kind of the seminal policy known as UCB1. So just to look at those terms more specifically, we see kind of a similar pattern as we saw before, where the first term, the mean, encourages exploitation. So if you have a very high mean reward, you're likely to always choose an action that has a high mean. This is kind of encouraged by this mean term in the UCB1. So just to be clear, we always search next in the potential node which has the highest UCB1 value. While this term here increases for nodes that have disproportionately not been searched. So in other words, this encourages the exploration of poorly searched and sampled actions. So this allows us to make reasoned decisions about how to explore different nodes in a decision tree. And so now Gabe is going to go into how we can combine. Yep. Oh,
Can I just a question?
Yeah, go for it.
So, so I think I see. This is based entirely on the random samples that you're taking.
Yes, exactly.
And you're not actually modeling any
No modeling at all.
distribution.
Exactly.
That. You're just
Yes.
taking the raw Monte Carlo samples, including just the mean, and then
Exactly. Yes. Yep. Okay. So Gabe is now going to go and talk to us how we can kind of combine UCB, so upper confidence bounds, and Monte Carlo simulation, put this all together and get a very kind of neat algorithm that can show us how to kind of perform collaboratively in the task that we're looking to do. There you go, Gabe.
Good. While Gabe is presenting,
Yeah.
do you mind just putting all of your names on the
Yes,
blackboard
I'll put
there?
them in
And then
order
that'll
that we
help
will see.
people when they're writing their comments.
All right, great. So so now that we've seen how random sampling can be used to ascertain the value of a particular state, and we've seen a selection criteria, UCB, which can be used to balance exploration and exploitation. I'm going to demonstrate how these can be combined into the main algorithm of our talk, Monte Carlo tree search. So I'm going to first go over the general framework for this algorithm. Then I'm going to demonstrate how it can be applied to extremely simplified single agent path planning problem. And then I'll also go over how it was recently applied to a very interesting problem of playing Go in DeepMind's AlphaGo Zero, before I turn it over to Jacob to talk about multi-agent path planning. So first of all, just to demystify the name a little bit, Monte Carlo tree search is a tree search, so you can think of it like BFS or A-star. It's assembling a tree where the nodes are states and connections are actions. And it's also using that random sampling that we just talked about to estimate sort of a heuristic that can be used to guide the construction of the tree. So Monte Carlo tree search contains 4 stages, and I'm going to sort of describe each one before solidifying the specific math that will be used for each one. So an important thing to note about Monte Carlo tree search is that there are sort of two policies that will be followed during a single round. So the tree policy is used while we're taking actions and states that are still in our tree that has already been assembled. And then our default policy is that sort of way that we ascertain the value of a state by doing a random simulation like we talked about before. So the selection phase uses the tree policy. So UCB at each level to determine an action to take within the tree. So we'll follow that policy all the way down, and I'll show you an example in a few slides. But we'll follow the tree policy all the way down until we reach a state that does not have all of its actions taken yet, and then we're going to add a node to the tree by taking that new action and evaluating the state that we produce and adding that as a node to the tree. So both of those stages, selection and expansion, are going to be following our tree policy. And now that we've added this new node, great, we've got this new state, but we don't know anything about its value, so we're going to use our default policy, which is essentially a random rollout. So we're going to do that rollout all the way to the what we've defined as the end of our simulation, and at that point we'll be able to evaluate from simulation the reward that we've received, and finally use that reward back propagation to update the estimated values of each of the parent states. Yes?
So is the root of the tree the last time step?
The root of the tree is the initial state.
Okay.
Yes. So all of these actions are being taken in simulation before any action is taken in the real world. So while Monte Carlo tree search is assembling its tree, the agent is assumed to just stay in the state of the root. Is that cool? So this slide illustrates exactly that. So our agent will be at some state, and then we're going to, in order to plan and select an action, we're going to run Monte Carlo tree search, which is going to assemble a tree where the root is the state, the current state in the real world of our agent, and we're going to run that 4-stage sequence many times, and each time a single node is added to the tree until we've assembled a large tree that, because of our selection criteria, as I'll illustrate soon, it will be unbalanced and deeper in more interesting areas, sort of. So after we've assembled this entire tree, we're going to use it to select an action based on the expected values of each action that's available to us at this state. We're going to obtain a new state, and then we're going to go back and continue to build our tree from that new state. So you'll notice that in my description, I maybe referenced UCB or random search as an example of how these different stages could be performed, but really they're not fundamentally characteristic of these stages. So there are many possible selection criteria or default policies that could be used to perform MCTS, and later we'll see that some of these heuristics, different selection criteria, or things that will enable a multi-agent setting can be plugged into MCTS to apply it to different problem domains. So a classical application of MCTS is combinatorial games. So in a combinatorial game, we have chess is a great example of a combinatorial game. So you can think about all of these things in the context of chess. So in chess, we have perfect information, so we know where all the pieces are at any time. Chess is deterministic, so if I take an action on a chessboard, it'll take me to the same next state each time. Chess is sequential, so there are two players in chess, but rather than moving simultaneously, they take turns making their moves. So we don't have to worry about what did the other player do while I was taking my turn. And chess is discrete time, so if I take some time to plan before I take my action, I can be confident that the world sort of has not continuously changed while I was planning. So all of these attributes make combinatorial games a prime application for MCTS, and you can see that chess, for example, has a very large state space, which sort of motivates the use of MCTS. We wouldn't want to assemble a whole breadth-first search tree in order to all the way to the very end of the game before we evaluate what action we should take for just like the first state, right? And we couldn't really use A* unless we had a great heuristic, which is hard to come by in combinatorial games like chess. But compare this to our multi-agent path planning problem. In the real world, when we're trying to solve this problem in Colombo, you can see that our problem will have partial information. So each glider may not know exactly the state of the world, and it may also have limited communication with other gliders and not know what they're up to. Our problem may be non-deterministic, so the same action may not always lead to the same state every time. Our multi-agent problem is simultaneous, so the gliders have to act simultaneously. And they might not know what the other one is doing when they make their selection of an action. And our multi-agent problem is continuous time. So while I'm planning, there might be some continuous phenomena in the environment that are changing. So in order to apply MCTS to this more simply at first, we're going to consider just a single agent problem with many simplifications. So we're going to assume there's just one glider, and it has perfect information about its environment, its actions, and deterministically transition to a state. It's by definition sequential because there's only one agent, so no need to even take turns. And we'll assume that our problem setting is discrete time, so we can plan a sequence of discrete actions and still arrive at an optimal policy. So to sort of solidify this environment, so we're going to use a discretized map over here, and you can see, we've broken up into a grid. Each grid space could have nothing, or a small circle, or a large circle, where the small circles are worth 0.1 reward, the large circles are worth 0.2, and the agent, this little red rocket, can go around and collect these rewards by taking actions, which could be motion in one step, either north, south, east, or west. We're going to assume there are no system dynamics, so the agent can just take these actions equally and freely at any time. We're going to assume a fixed mission duration. So maybe, for example, after 10 steps, we're going to say, okay, that's the reward that we're getting for this whole mission. And we're, of course, going to assume that there's just one single agent right here. So in order to apply MCTS to this problem, we're going to refer to the very first MCTS algorithm, upper confidence trees, and this algorithm uses the upper confidence bound, which we discussed before, as its selection criteria, and from that that determines its tree policy, and then it's going to use a random walk as its default policy to ascertain the value of a given state. So I'm going to walk through the application of this algorithm to this problem so that we can all sort of see how it works. So over here, again, we've got our state, right, which is represented by our vehicle's location and the locations of all these rewards, right? And then we're going to assume that we've already sort of run a few rounds of these four stages, and we've built up a little bit of a search tree to begin with. So at each node, we've kept track of the mean playout value that we obtained starting at that state, and we've also kept track of n, which is the number of times that state has been visited in our search, right? While it's been in the tree. So the first step that we're gonna the first stage of MCTS is selection, right? So we want to select a node in our currently built search tree to expand. So in order to do this, we're going to use UCB, right? Which, as we just discussed, is the mean, right, mu over here, plus the standard deviation, which is we're going to express as some function of the number of visitations to a given state, right? Which has also been tracked in our tree, and also the total amount of time that our algorithm has been running, or the total number of iterations that it's been running for, right? So you can see that as this nj on the bottom, which represents just an individual node's visitation count, increases, then our upper confidence bound is going to decrease because we're more confident that the mean is actually the true mean. We visited more times. But as our algorithm runs for longer and longer, this log of n is going to increase. So that's going to sort of balance out the increase in this and allow us to continue exploring with time. So we'll apply this upper confidence bound one level at a time. So you can see here we've actually plugged in the values, right? So mu over here, 0.3 for this node, and it's been visited once, and we've done 15 total steps so far. So we compute the upper confidence bound for each of these possible actions that will lead us to these new states from our root, which is our current state. And then, as we saw before, even though this node does not necessarily, this state does not necessarily have the highest expected reward, because we haven't visited it very much, we want to expand it. In this case, before we expand this second node over here, which has a higher expected reward, right? But we've visited it lots of times already, and we're pretty confident that it won't max out as high as this one. So that is sort of how exploration, it's an example of how exploration is being encouraged in this tree. Yeah?
How do you treat nodes where nj is 0?
So nj will always be 1, and we'll see why soon, but basically as soon as we add a node to the tree, we're going to immediately do a simulation, right? So expansion, we're adding a node, and then simulation, we're immediately simulating, and that will bring its count up to 1, and we'll have some sort of estimate of the mean for it. But so in this case, since we have n equals 1, we know that this node was just freshly added to the tree from maybe in one of the past couple rounds. So based on our upper confidence bound, we've now selected this action that takes us to this node, and because it's a leaf of the tree, we're now going to expand from it. So we zoom in. So this red highlighted node, we're just going to zoom in on it, and this is that same node with the same state, right? Mu of 0.3 n equals 1, and we've also zoomed in on our game map, so that we just see a little 3x3 section of it with the state of the vehicle being the state that's achieved at this node. And now that we've selected this node, we're going to expand it. So we're going to take a random action from this state and add the state that the next state that we obtain as a new node to our tree, right? And in simulation, we're going to have our agent actually move to that new state, right, and collect this big reward that was over there. So now we've added this new node, right, with an expansion, but we want to evaluate sort of what its value might be. So now we're going to switch from our tree policy over to our default policy and perform just a random rollout, where we take random actions and just look at what reward we come up with. So that little green squiggly line represents we're not adding any more new nodes to the tree as we visit new states, but we're going to simulate until we reach our time limit, and we're going to see what kind of reward did we get from doing that simulation. So that'll sort of give us an idea of the value of this state as well as all of its parents. And finally, we're going to do backpropagation, where we take that reward and we use it to update the mean and the visitation count of all of the parent nodes of the newly added one. Right, so then we're just going to repeat. So we're going to keep doing selection, expansion to build our tree, and then simulation, and adding one additional node representing a new state each time. So does anyone have any clarifying questions about that? Yeah.
First.
Oh, is the default policy necessarily deterministic?
So in our case, the default policy is random.
Okay.
So you want the default policy to have some randomness, because that way you can sort of explore the space well in that regard. But you're also doing exploration in just the tree policy based on the UCB, where you're trying to explore states that haven't been visited very much. But in our case, our default policy is just to take random moves. In some extensions, we can, and we'll see next with AlphaGo, they use a different sort of default policy. Yeah.
I'm not sure if there's an answer to this question, but just out of curiosity. So our UCB is a mix of a high mean and a certain value that we assign to nodes that have not been explored a lot, right?
Yes.
So my first question is, why is there not a weighting factor to weight this gain from exploration? And the second question is, why does this work at all even without a weighting factor?
Yeah. So in many applications there is a weighting factor, but in the derivation that I think we showed earlier from
I can note. So remember, I mentioned that there's a small value that decreases with time. Essentially, that is scaled also. So, but the usual scaling is that it's like to the -4. So basically, like so essentially, it's embedded. There's some type of scaling which is already embedded in that term, but you can add other scalings for specific applications, but it's not necessary in any cases.
Great. Yeah.
Just so I'm clear, which parts of this are random in the algorithm? So like the expansion was random, right?
Yes. So the default policy. When we did all the green steps, those were random actions being taken. But when we did the yellow step, that was part of our tree policy, which is based on the UCB, which is not random. Great. So after many rounds, we built up this tree, and you can see that a typical characteristic of a tree built by MCTS is that it's asymmetric, right? So we've explored more, you can see, into this high reward region where there are lots of big circles, and less over here where there are very few circles at all. And the reason is because as we've done our random rollouts, you might expect when we do a random rollout from this state over here, we're probably going to walk around this low reward region and estimate a low mean, right? Which has sort of happened. Whereas if we do a rollout from over here, we're going to walk around this high reward region, and then UCB is going to tell us, okay, explore more into that part of the tree. And then to perform execution, we're no longer going to care about exploration, so we're just going to pick the action which takes us to the highest expected reward state. So we might compare this to breadth first search. So if we were to apply breadth first search in this environment, our tree would basically just get built one layer at a time, right? We're all probably familiar with breadth first search, and you can see the actions that are in our tree are sort of all just achieving this like 2 steps away from the current state, right? But they're not really exploring into this high reward region. So it might be valuable to explore high reward regions for a number of reasons. The first is that potentially in a deterministic static environment, we could actually assemble our tree all the way to some goal state. So in chess, it might be possible to assemble a tree that extends all the way to a winning game, at which point, well, not chess because there are 2 players, but in some other deterministic environment, we might be able to assemble a tree that extends all the way to a winning state and then just take that sequence of actions to bring us to that state, right? And so we might want to achieve a certain depth to generate that full plan, but building a BFS tree to that depth would require a huge number of nodes. While with MCTS's focused search, we can achieve goals at a certain depth with a much smaller tree. But in a more realistic environment, we probably have some randomness or some dynamics or some other agents, in which case we're not necessarily certain that this sequence of actions is actually going to take us to this state. And in that case, what we're going to want to do is run MCTS from a state, then based on our simulations, we're going to select an action, and then by observing this new state that we see, we're going to continue building the tree, but only considering the part, we're going to sort of throw out the parts of the tree that are not applicable now that we've reached this state. So by biasing the construction of our tree more into states that we're likely to achieve next, we have to throw out less of the tree, and so we can build our tree more quickly. Yes.
This goes back a little bit. Are adversarial games generally considered to be deterministic, like chess, for example?
So I would say they are. So let's go back. So they are deterministic, but they are simultaneous. So
I'd say chess is definitely deterministic because any specific action taken by an agent has like the effect on the state of the game is fully determined by what that action. There isn't any like backgammon, for example, and you roll a dice and like you don't know what the next person's action set could be because it depends on some probabilistic element.
Okay. But you're not considering the other agent's policy to be stochastic.
yeah.
So generally in adversarial games, what you'll do is you'll assume that they're going to maximize their score and then you're going to maximize your score or something of that sort. So you choose moves that would be best for them.
Okay. Thank you.
But stochastic adversarial games do address that, and MCT applies to that.
Yeah.
So, in the example you're showing, you know all the rewards. How do you determine the rewards, like, in the water in the volcano?
So I think it sort of. So I guess there are two ways, right? So either we could be provided with all the rewards at the beginning, or we could sort of look back at last week's lecture on informative path planning, right, where sort of the agents are simultaneously mapping the environment and also trying to maximize their reward. So in that sort of scenario, it gets a little bit more complicated, but you can still sort of assign a reward value to visiting each location in the environment. Great. So some basic characteristics of the MCTS algorithm that we just introduced, UCT. It is aheuristic, which doesn't mean that there's no heuristic, but it means that there's no hand-defined heuristic. So what's happening is the search is being guided, but it's being guided based on this random sampling, this estimation of the mean, which is determined through simulation, where we're gathering random samples of possible rollouts. The search tree that's being built is also asymmetric, so as we saw, it'll focus more on interesting areas, which can be a benefit to us because we don't have to sort of build the whole tree in a combinatorially large fashion into all these uninteresting areas that we'll never visit. And the algorithm is anytime, which is useful because under time constraints we might not even know how long we have to run this algorithm, but fortunately, no matter how large of a tree we built, we still obtain sort of a value estimate for taking each possible action in the tree, and we can select an action based on that, even if we've run out of time to really build deep into the tree as we'd like. But although these are properties of the algorithm that I've just presented, MCTS is also modular, and different types of tree policy or default policy may sort of tweak these properties. So now I'm going to talk about a very recent application of MCTS that many of you may have heard of, AlphaGo Zero. So this is an algorithm that was produced by DeepMind a few years ago, and essentially it focuses on playing this game Go, which is a two-player combinatorial game. So in this game, there are two players, one with the black pieces and one with the white pieces, and they place pieces on the board to try to gain control, sort of the largest part of the board according to a set of rules, right? So we can see that this game will have a very many moves that you can take and a combinatorially large state space, so we wouldn't want to search through it all. It's a great application for MCTS, but even just sort of doing random rollouts in this environment is not going to give us a very good sense of how valuable each state is, and that's because the game is very long, and when we're doing these random rollouts, we'd sort of like to rather than just taking random actions, be guided by some sort of additional heuristic that will lead us into even more interesting parts of the tree even faster, because it's just so large, right? So the way that AlphaGo Zero addresses this is they use a neural network to sort of inform the default rollout policy of MCTS. So this is a figure from the AlphaGo Zero paper, and you can see it's very, very similar to the stages of MCTS that we just discussed in the most basic case. And so they maintain this tree that consists of states of the Go game, and they perform selection based on actually the upper confidence bound, right? Which is this Q, which is the estimated value of a particular state based on rollouts, and U, which is exploration term based on the visitation count of this state. But the big innovation here is that once we expand a state and we want to evaluate we want to obtain an estimate of the value of that state, instead of just doing a random rollout, our rollout is going to be guided by this neural network that's been trained on all of the states that we've seen so far and their values. And so what this enables us to do is to, first of all, store some information about states that we've observed on our way to a big reward without explicitly putting them in the tree. So the neural network is going to allow us to keep our tree small, but also retain some information about some states that we've seen way further down. And secondly, our neural network is going to be able to generalize to even new states that have not been seen before by identifying features that are shared among valuable states and using that to inform its rollout. So action selection here is done randomly, so the neural network produces probabilities of taking different actions as you proceed, and in that way we continue to sort of sample from this non-deterministic distribution of possible values, but we get a better estimate of what might be obtained if we take some good actions starting in this state. And when we back up, we're going to update these explicitly maintained Q values, but we're also going to train our neural network so it becomes better at doing these rollouts. And what DeepMind observed is that AlphaGo Zero, which combined MCTS with neural networks, actually outperformed not only the best human players, but also the best algorithms which used some sort of search with a hand-coded heuristic that was maybe designed to help them out. So the big claim here is that AlphaGo Zero had almost no built-in knowledge about what constitutes a good strategy in Go, and yet it was able to outperform pretty much all other existing players, computer or human, and in fact it even came up with some new strategies that are now actively studied by professional Go players. So now that we've seen the application of MCTS in the single agent path planning, yes.
Quick question. But it's still, in the end, it still didn't require the bootstrapping?
What do you mean by the bootstrapping?
Well, I mean, so initially it used a prior policy, right? That you said, which was hand coded, right? And that's what I thought. That's what it used to start bootstrapping the learning of a more effective heuristic.
No, so there was no prior policy encoded. It was assembling a tree just like in MCTS, and at first the neural network didn't have any information about what constitutes a good board, so it was just sort of taking random moves in these rollouts. But as more states were added to the tree and their values were evaluated through these rollouts, the neural net was trained on those to become better at selecting policy. That's how I interpreted it.
That's what AlphaGo Zero did.
Yeah.
Yeah.
But AlphaGo,
the original AlphaGo Master was trained on
Oh.
games of like professional players,
But then the like Alpha Zero, which was also been applied to chess and like shogi, they basically start with no prior like expert policy like to
Okay, so
train.
they didn't have
everyone.
a right.
Yeah, yeah, no
Yeah.
prior.
And with AlphaGo Zero, they basically keep track of kind of the best candidate at that point, or the best like neural net at that point, and then they compete against each other. And once you get a sufficient number of wins against the previous best, then you are now the best. And you continue self-play. So they just do a ton of self-play with just the rules of the game instead of expert human moves.
What is the number of self-play?
The number of
Number of self-played games.
I have no idea.
Definitely like
40,
in the
40 million
millions.
worth of time.
In
It's like
3
like
days, it played 4.9 million games against itself.
Wikipedia has a lot. Because they can afford to do just so many simulations. So.
Great, so now I'm going to pass it off to Jacob, who's going to tell us about how MCTS can be applied to multi-agent path planning.
Cool. Thanks. Okay, so I think part of what we wanted to drive home with that AlphaGo Zero kind of discussion, A, that it's cool and it's exciting, but also B, that a lot of the most promising and effective kind of utilizations of MCTS are when we kind of get away from this kind of canonical MCTS and kind of introduce other elements and other kind of modular elements in here to improve certain parts of the MCTS algorithm. So that's kind of a key insight, and most of it's something that we're going to kind of draw on as well for collaborative, so we're going to work to improve kind of our default policy and kind of some other aspects of the MCTS algorithm. So the extension of collaboration is fairly straightforward. We previously had this kind of map here, and we had a single agent exploring. Obviously, it'd be better and more time efficient, more energy efficient, more everything efficient if we had multiple agents. So we're going to kind of transform that into our discretized version here, and we're just going to add a couple extra gliders, and then we are done. Excellent. Okay, cool. Not quite, because by adding some of these gliders, what we've done is we've violated some of the assumptions we made previously. So we showed you earlier these kind of 4 characteristics that we were looking at, and we told you that MCTS for our kind of situation was perfect information, deterministic, sequential, and discrete. So we're going to stick with the perfect information and deterministic kind of criteria here, but we've now, by adding multiple agents, we've made it continuous time. And this discrete and continuous time, I don't love the terminology here. We drew it from a survey, so I just want to kind of hammer down exactly what we mean by this. In discrete time is essentially that if I don't take an action, the world does not change. Nothing will happen until I take an action. And so in chess, for example, the world will not change until I take an action. In continuous time, the world changes regardless of whether I take an action or not. And so the result of that is that we kind of have a limited time to plan. If I just sit here and think about things forever, the world will change around me and then my plan will no longer be valid. So this means that if we assume continuous time, which we assume continuous time means we now have multiple agents that are making decisions kind of independently from each other or potentially independently from each other, we need to assume continuous time, so we have a limited time to plan. It also means that upon each iteration of planning, we probably want to remake the tree. And that's because our previous tree may no longer be valid because the state has changed around us despite the fact that we have not made an action. Does that all make sense? Is everybody clear on that? Excellent. The other kind of criteria that we violated, or assumption we violated here, is that it's no longer we're no longer sequential. When we had only one agent making a decision, that agent would essentially be every single depth in the tree was that agent making a new decision. With multiple agents, we're going to have each one kind of making decisions simultaneously, so we can no longer, it's unclear if we can still plan in the same way. And so the question becomes, does the non-sequential aspect of actions of the agents matter? And the short answer is probably not. And so we can look at this 2010 paper by Samothrakis. And so basically they applied MCTS to a game called Tron. So Tron is a game where 2 players compete to try to trap the other one and force the other player to run into either themselves or the wall or whatever. And it's done simultaneously. So both players take action simultaneously. And they coded up an MCTS version of this where they had each player move sequentially. And they found that despite this sequential choice of actions, that at the University of Waterloo Tron competition, the best versions of MCTS, so kind of a spoofed up version of MCTS, performed comparably to other approaches. And so basically this suggested to them that despite the fact that it's a simultaneous game, even if they are planning sequentially, it was still fine, they still performed well. So then that means that we can kind of assume these criteria, so we have perfect information deterministic still, but we can now take a simultaneous and continuous time game, and we can then apply MCTS to it for our collaborative search. So within collaborative MCTS, there's 3 kind of major things that I'm going to talk about. We're going to talk about MaxN, which is a variant of MCTS for multiple agents. We're going to discuss decentralizing MCTS, and finally how to improve the default policy. I want to point out this competition. This is the Miss Pac-Man competition that we talked to you about briefly at the very beginning of the lecture. This was created by Simon Lucas in 2007, and this has created a lot of research that we're going to draw very heavily upon in this section of the talk. And the reason that this is such a good example for us is it actually shares basically the same exact assumptions that we've been making for our problem. So it is perfect information, deterministic, simultaneous, continuous time, and the ghosts work collaboratively to eat Miss Pac-Man. So because of this, it's a very good kind of platform for us to develop algorithms on that we can then apply. So this is the original tree structure that we've been kind of working with. We have agent 1 goes again and again and again. They just make decisions sequentially. We have actions that are represented by the lines, and the nodes or the states represented by the circles. In MaxN, the only difference, or excuse me, taking a step back, we're going to leverage the finding from the Tron paper so that instead of having agent 1 make a decision sequentially, we're going to have agent 1 plan their action, then agent 2 plan their action, then agent 3 plan their action. So this is that sequential planning despite the fact that it's a simultaneous game. Then we're going to modify this for MaxN. So MaxN basically says instead of returning a single value at each node, as Gabe was discussing, we're going to return an n tuple of values for n agents. And the reason we do this is that each agent can have a different reward at each point, but we want to keep track of all of their rewards separately. And so then basically we can have a situation where the tree policy and default policy will remain the same, but at each point, if agent 2, for example, were to make a move, they would get a reward, but agent 1 and 3's reward would not change, and then they move to the next move. Cool. So we can keep the same tree policy, we can keep the same default policy. The question becomes, how do we choose an action once we've planned? So everything else is the same. We're now choosing an action. We've kind of made our plan, made our tree. In canonical MaxN, players are adversarial, so they had to develop a bunch of strategies to choose which action is best. But because our agents are collaborative, it makes sense that we can just choose the sum of the scores. So in this case, agent 2 is going to choose the one that sums all of the scores to the highest value, the max of the sum of the scores. And this is kind of an interesting case here because despite the fact that agent 2 would most benefit itself from choosing the middle node there, which would give it a value of 4, it chooses the first node because it recognizes that by choosing that, the other agents will have higher scores in total. Additionally, because this is a simultaneous game, not only do we want agent 2 to choose its action, we actually want agent 3 and agent 1 to choose their actions as well. So we'll go ahead and choose 3 actions at once, or n actions at once, depending on how many agents there are, and let them all execute those simultaneously, and then we'll go ahead and replan the tree. Cool. So that's kind of collaboration in a MaxN sense. Benefits, it's simple, it's modular. We can kind of shove in any default or tree policy that we've been talking about to improve this. The disadvantage, though, is that it requires robust communication between the agents and the master. And as you've kind of may remember, we may not have this in our situation. So we've talked a lot about using these gliders as our workhorse or our vehicle to do the exploration. As they kind of go underwater and dip around, they may lose communication between themselves and the master. So then what happens is if we have this central planner that's creating this tree and then passing out information to all these other gliders, we require that they get frequent communication between the glider and the central planner. We also require that the glider frequently updates the central planner on kind of what's happening in its local environment. With infrequent communication or a kind of unrobust communication, this may not be feasible. So what our desire then is that we actually hand over control authority to the agents. And so basically we may still have a central planner, but we're going to allow each agent to plan independently. So each agent will essentially have its own brain and be able to think independently, and that way if this communication does break down, the agent can still perform adequately in this scenario. So this kind of, we're going to refer to this a lot. This is going to be a cartoon schematic of kind of this the MCTS for collaboration. So we'll have 3 different agents. They're each going to make a multi-agent plan, so they're not going to just plan for themselves. They'll plan for what they think everybody else is doing and kind of take the sum of the max n of the scores, as we discussed. Then they're going to take some action. Okay? So each agent plans individually and then takes some action individually. As I mentioned, each agent's tree is actually a multi-agent tree. It's not a single agent tree. We can keep the tree policy as UCB, that's fine, and we can keep the default policy for now as a random simulation for each agent, so just this like kind of random walk. If we look at this, this actually looks like a form of parallelization, and so this is something that's been kind of readily studied within MCTS. It's kind of different forms of parallelization. And so we can take a brief aside to look at the forms of parallelization within MCTS. There are 3 major types with the kind of variant on the last one. The first one is this what's called leaf parallelization. And so in this case, we have some central planner that kind of holds a tree, and there's only a single tree. It performs UCB or whatever kind of selection criteria to get down to a node, and then when it's running simulations from that node, it runs 4 simulations instead of 1 simulation. So in this case, we have basically our central planner, and while this survey paper conceived of these as threads, we can conceive of these as our gliders or our individual agents. In root parallelization, each agent has its own tree and performs the MCTS on its own tree. In tree parallelization with a global mutex, we basically have the key insight here is that while agent is traversing the tree, we don't want to corrupt the data, so we want to lock that tree. But we can have, even while one agent is traversing the tree, we can have other agents that are performing simulations. And so that's not going to affect the choice that a single agent is making as it traverses the tree, and therefore we can kind of run this in parallel. And then finally, instead of locking the whole tree, we can only lock the individual node that agent is on, and we can still have multiple agents performing simulation as well as multiple agents performing kind of this traversal of the tree. So in 3 of these 4 cases, what you see is that we have a central planner that is holding kind of all the decision-making authority. There's like one single tree, and even though we have multiple agents kind of traversing that tree, we do have this central planner. Only in root parallelization do we kind of have the architecture that we were looking for, where there's no one individual central planner. We actually just have multiple agents making decisions. So there's a couple additional steps in root parallelization. After each agent has made its plan, they'll kind of send their votes off to this central planner, and they'll vote on some action sequence. And the action sequence with the highest number of votes is taken. And there was a paper in 2010 by Suejima et al. That showed the evidence that this majority voting scheme gives a better performance than conventional approaches. And they hypothesized that this is because root parallelization, which is utilizes a unique random seed for each tree, kind of escapes local optima better. So not only do we have a situation where root parallelization kind of has a decentralized architecture, which is what we wanted, there's evidence that it may perform better than conventional approaches. So this is excellent.
And when you say better,
yes,
can you quantify at all how much better? A little bit better? A lot of it better?
We'll get into that a little bit later. There's a graph I can show you. It's marginal, I would say. Yes?
So those trees just in the figure, they look the same. In general, are the trees like could be totally different?
They could be totally different. And so I actually was just talking to my group members about this. The random seed is not on the exploration or the selection policy, right? They're still going to apply UCB. The random seed is on the simulation policy. And so what that means is that you'll get slightly different simulation results, which may result in a slightly different tree being built. For the purposes of this figure, they did build basically identical trees. Not my figure, so it's a good question. But yeah, in theory, the trees could grow in very different ways. Cool. So back to this cartoon schematic. We have 3 different agents. They're making a multi-agent plan. Then they're proposing a desired action. We're going to communicate that desired action to the central planner. We're going to then communicate that we're going to all vote whichever gets the highest number of votes will select, and will communicate that action sequence out to the gliders along with some updated states. So two problems, yeah.
I thought the point was you were trying to get rid of the essential planners.
You're
so.
too good. Yes, number 2. Okay, so kind of 2 problems with this. First, we're using random playouts for our default policy. We can do better. But secondly, to your point, we've seemingly reintroduced the need for robust communication. So we're going to address the random playout as a default policy first, if that's okay with you, and we will get back to the need for robust communication. Cool. So I want to turn again to Miss Pac-Man competition. To improve the default policy, they kind of had an insight, which is that we can pass action sequences from other agents to each agent in the simulation phase. And so what this looks like is in our original tree, let's say we've just taken an action, so that's that little action block, and we've now moved down to this new node, and we're going to start rebuilding our tree. So we're rebuilding from scratch. We choose some action, and we start expanding that action. We expand to that action, and then we run our default policy, which was originally random moves. So that may end up looking something like this. So we take a bunch of random moves, and then we return some n-tuple, in this case 3, score that basically is the result or the reward from taking those random moves. The insight that they had was that from our previous trees, we actually already have a good guess at the actions that all the agents would have taken, right? Because they've already made a plan. And so what we can do is, instead of taking these random moves in simulation, we can actually use the known moves. So instead, the known moves may have been that agent 2 is going to move there, agent 3 was going to move there, and agent 1 was going to move there. And so in simulation, what we'll do is we'll actually use the predetermined action sequence, play that out until we run out of moves, and then we'll choose moves randomly. And what they found is this improved performance because the simulation was more accurate in some sense, because it's no longer purely random. Cool. So back to our cartoon schematic. We have each agent, multi-agent plan, desired action, vote, and then finally, instead of passing a single action back to the agent, we're going to pass the action sequences from all the other agents, and they can use that to improve their default policy and improve their simulation. Great. On to your question. What happens when communication fails? So instead of now basically having some sort of voting mechanism, we have each agent is going to simply take that action. And so this was actually explored by a paper in 2018 by Best. And so they investigated a spoofed up version of MCTS. So I want to clarify that there are some differences between the architecture I've been proposing or we've been proposing here versus what they did. They used MCTS to grow some search tree. They then passed not a deterministic action sequence, as we've been talking about, but they passed a probabilistic action sequence. And then when available, they would communicate that probabilistic action sequence between the robots to help them with their simulation policy. Cool. This was their environment. As you can see, it looks, this is like their test environment. It looks drastically similar to the environment that we were using here. So they basically had multiple agents. They had some obstacles. They had some rewards that were scattered about this area. And they asked their algorithm to plan to maximize the reward each of these agents was going to, or the sum total of the agents was going to receive. And this is to your point. They graphed here the improvement on what they're calling decentralized MCTS as compared to centralized MCTS, which would just be the kind of default algorithm we've been talking about. And on the x-axis here, they have communication failure probability. So when there was no failure of communication, when every single message between the robots got through, they found that their version of decentralized MCTS performed also slightly, marginally, I would say, better than the centralized version. But they found that even when the communication was failing very often, so almost 100% of the time, that the single agent was still able to make reasonable plans and reasonable choices for themselves, and that they could get reasonable performance on the whole. Excellent. So, yeah.
In this environment, was the reward the same, even if multiple robots sent or went to the same location?
I don't know. My guess from having skimmed is that once you've visited a reward, it disappears. Yes, correct.
Any other questions?
Okay. So in summary, we have some sort of central planner, we have some sort of gliders, each of which has its own control authority, makes its own, runs its own MCTS, incorporating whatever heuristics and performance boosting modifications it needs. When communication allows, we're going to communicate action sequences between the glider and the central planar. And then finally, these action sequences can be incorporated into the local agent's MCTS. Excellent. Are there any questions?
This may sound a little silly, but with the decentralized MCTS, it seems a little needlessly complicated. I mean, I don't know, since the 60s or whatever, there's been pretty standard ways of doing in adversarial games, for instance, you just have one, do basically a recursion, sort of. It seems like there's no reason you can't use just those sorts of very standard techniques here. I mean, I guess it seems like the hard part is handling communication, not lack of communication. I felt like we were kind of going in an order that was a little counterintuitive, but I might just not be understanding.
Yeah, I don't think I know enough about these 1960s approaches to path planning and multi-agent path planning to answer that appropriately. Does anybody else in my group know enough about that?
I didn't mean path planning, I just meant things like chess.
Okay.
The standard way you do that is you run planner. This is mini-max.
Right, sure. So I think Felipas can speak better, more appropriately about this, but just kind of on a baseline level, the reason why MCTS works is because it grows the tree very asymmetrically. So when you have a very large state space like chess, if you were to use breadth first or even minimax, you don't prune enough to actually search the space well.
Oh, of course. I wasn't saying. I mean, MCTS is obviously a great algorithm. I just meant for the multi-agent thing specifically.
Yeah.
I mean, if you're doing something collaborative, generally it's minimax, something like it's max or whatever. But I honestly don't know enough about kind of where that comes in to be able to say why one may want to avoid some of those kind of regressive techniques.
Okay.
Good question.
Any other questions? Okay, if there are no other questions, we're going to have our last two group members come up briefly and talk about the homework assignment and kind of give you a preview of what y'all are talking about. Go. Zach.
So a quick primer on the mini piece set for our team. So 2 parts. First part will focus primarily on the kind of the backbone of MCTS that my group mates have presented today, and that's going to be the selection, expansion, simulation, and backpropagation. So you guys will code up each of those functions, and that will be in the context of the Gomoku game, which is basically like tic-tac-toe, but you need to get 5 in a row, and it's a bigger board. But we'll have some more details on that as well. And then part 2 of the piece set goes into, all right, now that we have this kind of backbone of MCTS implemented, now we're going to try to use that for collaboration. We'll use a test bed similar to what we talked about today, where we'll have discrete states. We have values kind of scattered throughout this region. And then you need to implement some basic helper methods to represent the game state and retrieve the next possible action sequence for a given node in the graph. And then we'll have some visualizations up there so you can see how the robots are navigating the space. Do you want to add anything?
Yeah, it may take relatively longer time to execute the program, so you should start earlier. And it takes about 30 seconds to determine a single move in that Gomoku game. But you don't start from an empty board. We don't want you to spend like half an hour to really play a game. So it starts halfway. But it will take around 3 minutes to complete the game, in about 6 steps. But you should not start from the last minute.
Right.
So why should we do your problem set? So one, what will we learn, and why will we have a blast doing it?
First, it looks fancy. We have very beautiful figures and visualization for most problems. And second, we have you can in the first part you will build the core MCTS part. It's very short. So it's very short. It's very relaxing, and you can get the core MCTS part the 4 functions, the selection, expansion, and simulation and backpropagation down. And then you know clearly how it works, and we have written all the wrappers for you, so it's very convenient. And in the second part, you will get to know how to apply the code you built in the first part to how to. It's modular. The first part has nothing to do with the second part, but you can change the second part to change the environment. How you then you can plug a different setup to the MCTS.
Zach, anything to add?
I'll say you'll also learn a bit, have a better intuitive understanding on when MCTS is applicable, what kind of problems they'll perform well on, what they won't perform well on, and introduction of like what kind of heuristics can help your default rollout policy, and stuff like that. So, yeah, should be a very fun experience.
Great. One last question. So what are we likely to see in terms of these ideas in final project?
Excellent question. Have we discussed this? Very limited amount.
Yeah, we will see. I suppose we will.
We will.
Try to be applying,
with bated breath.
I think we'll be trying to apply more of the kind of the elements talked to by Jacob, the collaborative elements, and I think I would find it interesting to see if we can apply some something a little more heuristic, some interesting heuristics to it to see if we can apply that. But that's kind of something that's interesting.
Actually, that reminds me of a question. Are any, like, this is a heuristic, like you mentioned the idea of admissible heuristics at the
Yes.
beginning. Is any of this like admissible in some sense, or is there explanation to the idea of admissibility? You kind of described the rollout as being kind of like a form of heuristic.
Yes. Normally during like the rollout policy, kind of the base case for us that we introduced, which is purely random, so like a uniform sampling. But when we say heuristic, we don't necessarily need it to be like an admissible in the sense of like an A-star heuristic. But in this case, it's more of like a bias. We're introducing like a bias towards like what your rollout would be. And in some sense, it's like you can do a weighting factor there where like sometimes it's just purely random, or sometimes we follow this bias that we inject into it. And again, it's more just to like lead it along the way to get better values to propagate back up. But you don't, in that sense, need admissibility.
But can I just to add to that, I think so. You can imagine for A-star where you have a cost, and you want to always make sure that you're underestimating the cost. Here, it's the opposite of cost. You have reward, but we will never overestimate the reward, basically, because you're not necessarily going to be unless you choose the optimal policy. You can never get a policy that's more optimal than the policy you had in the first place. So I think that should.
It kind of reminds me of actually thinking of like RRT star, it's kind of like probabilistically complete and optimal after some long enough time to roll out. That's a fair comparison.
Yeah, in the main paper that we drew from, like the kind of the survey paper overview of MCTS, does have a bunch of similarities between like an RRT approach.
Just to kind of add on to that, there is one just unbelievably excellent survey paper. So if any of you want to kind of get a brief overview of this and in a maybe more structured way than we had covered it, I would go to this survey paper, and it's in our slides. So when they're released, you'll be able to see them. But it's at the bottom of one of these slides. It's this one right here.
Brown
2012. Brown 2012. Excellent.
Excellent. Thank you very much. Okay, so we have one.